Hello and welcome back. In this video we are going to discuss an example of solving an initial value problem using Laplace transform, and we are going to involve a piecewise defined function in this example. So let's see the example. So we want to solve x double prime t plus xt, this x is a function of t, equal to ft, and value of x at point 0 is 0 and value of first derivative at 0 is also 0, and this function ft is defined as 1 if t is between 1 and 5 and 0 otherwise. And we want to solve this ODE using our Laplace transform, and you'll see how easy it is to solve using Laplace transform. Okay, so let's start. So our first step is we take the Laplace both sides. So Laplace of double derivative is s square, xs is the Laplace of xt, minus s times value at 0 minus x prime 0, and this here is our Laplace of double derivative, plus Laplace of xt, which is going to be xs by our notation, and this is equal to Laplace of ft. Okay, so we want to evaluate this Laplace of ft, and how we will do that? So let's focus on Laplace of ft first. So first we want to write this ft in terms of our known function, and we will use our Heaviside function. Okay, so what we have is this function is non-zero in the interval 1 to 5, everywhere else it is 0, and it is 1 in this interval, right? So first we can write u of t minus 1. It means this function is 0 if we are talking about the values less than 1, and it's greater than 0 if we are talking about the values greater than 1. But we want it to be 0 after 5, right? So what we will do is we will subtract Heaviside function of t minus 5. So if we take the values greater than 5, then 1 minus 1 will give us 0, right? And then Laplace transform of ft by linearity is equal to Laplace transform of ut minus 1 minus Laplace transform of u t minus 5. To find the Laplace transform of u t minus 1 and t minus 5, we can use our table, which says it's going to be e power negative 1s, so we can just say okay, negative s divided by s plus minus the in between sign is negative, e power negative 5s divided by s. Using our table, we found out the value of Laplace of ft. Okay, now we will plug in this value in our equation over here. So what we will get? So observe here that since x0 is 0, this value is 0. Since x prime 0 is 0, this value is 0, right? So what we are left with is s square xs plus xs equal to e power negative s divided by s minus e power negative 5s divided by s, right? If we pull out xs, we'll have s square plus 1 e power negative s divided by s minus e power negative 5s divided by s, right? We pull out s square, we pull out xs to get s square minus 1 because we want to solve for xs. Now we will divide by the coefficient of xs. Remember the steps? We take the Laplace transpose, we find out the value of xs, and then we take Laplace inverse. So we have e power negative s divided by s times s square plus 1 minus e power negative 5s divided by s times s square plus 1. And now we want to take inverse Laplace transpose. So let's take it term by term. So inverse Laplace transpose of 1 over s times s square plus 1. This verify that, so you need to use the partial fraction to find out this Laplace inverse and verify that this is equal to 1 minus cosine t. Okay, so this is your exercise. You need to verify this and you will need to use partial fraction to find out the Laplace inverse of this function. Okay, so now next we wanted to find out Laplace inverse of e power negative s. So we are going to use the Laplace inverse of above function, and now we are just giving it a shift, e power negative s divided by s times s square plus 1. So here we are using the shift operator. So we are using second shift. Let me write down what second shift property was, just to recall. So in the second shift we had Laplace of a function ft times u of t minus a is equal to e power negative as Laplace of t plus a. Oh, I forgot the Laplace sign. I should say this is Laplace of this function, right? Okay. So if we take Laplace inverse both sides, let me simplify one further step so that you can see it clearly. So this function can be written as Laplace inverse of e power negative s times Laplace of 1 minus cosine t, right? So here you have the value of a equal to 1, and now we are going to use second shift, this formula over here in blue. So using this shift property, we will get this is equal to 1 minus cosine, in place of t we'll replace it by t minus 1. Okay. And u of t minus 1, this is our ft, and u of t minus 1, right? So this is the Laplace inverse for the first term. Similarly, we can calculate the Laplace inverse for the second term, which is e power negative 5s divided by s times s square plus 1. So this term can be written as Laplace inverse of e power negative 5s times Laplace of 1 minus cosine t. Okay, and then we use second shift and using the second shift, this time our value of a is equal to 5. So we have t minus 5, 1 minus cosine of t minus 5 times u of t minus 5, right? So now we know Laplace transform of both of these terms, and Laplace transform of xs is xt. So we got xt is equal to 1 minus cosine of t minus 1 multiplied by u of t minus 1 minus 1 minus cosine of t minus 5 multiplied with u of t minus 5. And this is our answer. This is our solution for the IBP. Okay, so this is how we deal with the piecewise functions. So first we write down the piecewise function in terms of Heaviside function. We take the Laplace transform both sides, find out the value of xs. We take Laplace inverse both sides, and then you will need to use the second shift property and we find out our solution finally. Okay, and we stop here today and we'll meet in the next video. Bye bye.